This is Dr. Sankar Reddy, Professor of Civil Engineering, Lord's Institute of Engineering and Technology, Hyderabad. Today, the content that I have taken for the discussion is mixed design by American Concrete Institute method. So, for the mixed design by ACI method, the data required is sieve analysis of coarse and fine aggregates, dry density of coarse aggregate, bulk specific gravities and also moisture content of coarse and fine aggregates, mixing water requirement for a concrete, specific gravities of a cements and other cementitious materials if we use, and also another important content which we need for us is relationship between strength and water cement ratio or ratio of water to cement plus any other cementitious materials for available combinations of the cements and if considered, and also the aggregates. Step 1, choice of a slump. If a slump was not specified, the value of the slump that we should be considered was mentioned in the table 1 for various types of concretes when the vibration is used. Suppose for reinforced foundation walls and footings, the minimum slump that we should be considered for the design is 25 millimeters and the maximum slump is 75 millimeters. Plain footings, caissons and substructure walls, slump values we should be take is 25 minimum, 75 maximum. Beams and reinforced walls 25 and 100, building columns 25 and 100, pavements and slabs 25 and 75. For mass concrete structures, the value of the slump that we should be take is minimum 25 and also maximum 50 mm. Other than vibration, for if we consolidate the concrete, the slump value should be increased to addition 25 millimeters. Now this is the process how we can find the slump in the field. Now coming to the maximum size of the aggregate. So here ACI 211.191 specifies some specifications to us to choose the maximum size of the aggregate. First specification is 1/5 of the narrowest dimensions between the sides of the forms. Second one, 1/3 the depth of the slabs. 3/4 of a minimum clear spacing between individual reinforcing bars or bundles of bars or pre-tensioning stands. Now this is the coarse aggregate we are observing in the figure stack. Now come to the mixing water and also the air content. It purely based on the nominal maximum size of the aggregate, particle or maybe shape of the aggregate, grading of the aggregates, concrete temperature, amount of entrained air and admixtures if any. If here I have given the two tables, table 2 and table 3, which provides the requirement of water content for the concrete purely based on the maximum size of the aggregate for both non-air entrained and air entrained. If the slump value is in between 25 and 50 millimeters, if the size of the aggregate is 9.5 millimeters, the amount of water that we should be considered for the concrete is 207 kg per meter cube. If the slump value is in between 75 and 100, if the size of the aggregate is 19 mm or 20 millimeters, the value of the water that we should be take is 205 kg per meter cube. If the slump value is in between 150 and 175, if the size of the aggregate is 37.50 millimeters, the amount of water which required for us to make the concrete is 190 kg per meter cubed. Now here, this is the process. Come to the average total air content for different level of exposure. Now for mild exposure, if the size of the aggregate is 9.5 mm, the amount of air content that we should be consider is 4.5%. If it is a moderate exposure, if the size of the aggregate is 19 mm or 20 mm, the percentage of air content that we should be take for the design by ACI method is 5%. If it is severe exposure, size of the aggregate is 20 millimeters, the percentage of air content that we should be consider is 6%. Now here, this is the process of mixing water at the site for making the concrete. Now come to selection of the water cement ratio. So here selection of the water cement ratio we have shown in the table 4 purely based on the compressive strength of the concrete, and also for different exposure conditions, freezing and thawing, and also for the seawater exposure, we can select the water cement ratio from the table 5. Here table 4 meant for selection of the water cement ratio based on the compressive strength of the concrete, whereas table 5 present the selection of the water cement ratio based on the exposure conditions. Now here you see, if the compressive strength of the concrete after 28 days it is 41.40 megapascal. For non-air entrained, the water cement ratio that we should be take is 0.41. Suppose if the compressive strength of the concrete is 27.6 megapascal or 27.6 Newton per millimeter square, if air entrained, the value of water cement ratio that we should be considered for the design is 0.48. In the same way, if the compressive strength is 20.7 megapascal, non-air entrained, the value of water cement ratio that we can be considered is 0.68. Now here, for maximum possible water cement ratios for the exposure conditions, suppose now if you take the type of the structure, thin sections like railings, curbs, sills, ledges or ornamental works, and sections with less than 25 mm cover over the steel. Suppose if it is exposed to freezing and thawing, the value of water cement ratio we should be considered is 0.45, whereas structure exposed to seawater, for these structures the value of water cement ratio that we should be take is 0.40. For all other types of structures, if it is exposed to freezing and thawing, the water cement ratio we can be take is 0.50, whereas for the structures exposed to seawater, the water cement ratio we should be take is 0.45. Now here, so here this is the snap which indicates the mixing of water to cement ratio. Now come to calculation of the cement content. Already we know how we can be collect the water cement ratio based on the exposure condition and also compressive strength of the concrete, and also we know the collection of this amount of water which is required for the concrete based on the size of the aggregate and also slump. Once we know the value, then calculation of the cement, we know water cement ratio equals to ratio of water to cement. Here we know the value of quantity of water which is required for the concrete, and also we know the value of water cement ratio. From this relation we can get the value of cement, amount of cement which is required for the concrete in terms of kg per meter cube. Now here you see the how we can be store the cement bags at the site before going for concreting work. Now come to estimation of the coarse aggregate. Here we have given the table 6. It purely based on the, here we should collect the value of volume of coarse aggregate which is required for a volume of total aggregate which was present in the concrete. Now come to here, if the size of the aggregate is 9.50, if the fineness modulus of the fine aggregate is 2.40, so the coarse aggregate is 0.5 times of per unit volume of the concrete. Now come to, if the size of the aggregate is 12.50, if the fineness modulus of fine aggregate is 2.60, So the volume of the coarse aggregate that we should be consider is 0.5 times 57 times of volume of the concrete. In the same way, if the size of the aggregate is 20 millimeters and if the fineness modulus of the fine aggregate is 2.80, the volume of the coarse aggregate is 0.62 times of volume of the concrete. Now here, this is the coarse aggregate stack or maybe coarse aggregate. Now come to estimation of the fine aggregate. So here we have two methods to find out the fine aggregate quantity. The best method what we have, we can be know is volume method. Now here in volume method, once the volumes of the aggregates we know how we can be find out the weights of each ingredient which is present in the concrete based on the values of specific gravities of that ingredients. So here, now come to, this is the stack which represents fine aggregate. Now come to adjustments of the aggregate moisture content. So here aggregate volumes are mainly computed based on dry unit weights, but aggregate is typically batched based on the actual weight of aggregate. Now here any moisture present in the aggregate will increases, we know that it's the weight of the aggregate. So here what happens is due to effect of moisture content which was presented in the aggregate. So here we should do the corrections. If we didn't do the corrections, the weight what we can be get is incorrect or volumes which we can be calculated is incorrect. Now here this is the process moisture content which was presented in the aggregate or maybe aggregates water content. First one, if it is a oven dry aggregate. Second one, if it is filled with the air. Third one, it is a saturated. And the last one is a wet, purely wet, totally occupied by the air or moisture content. Now come to trial batch adjustments. This is the more important. Once the calculations were made, then we should be go for one trial mix. So based on the trial mix, why we should be do the trial mix is to adjust the desired slump. It should be free from the segregation problem and also finish ability and unit weight, air content and also strength of the concrete. Now come to here, for easy understanding the methodology which I was explained to you, we take one worked out example so that you can follow very easily. Now I will read out the problem that we are going to be work out. We require a mix with a mean 28 days compressive strength. It is measured on a standard cylinders of 35 megapascal and a slump of 50 millimeters. Ordinary Portland cement is used. The maximum size of a well-shaped angular aggregate is 20 millimeters. Its bulk density is 1600 kg per meter cube and a specific gravity is 2.64. The available fine aggregate has a fineness modulus of 2.60 and a specific gravity of 2.58. No air entrainment is required. For the sake of completeness, all the steps, even when obvious, will be given. Now you observe, we can be work out the problem. First, first step is the choice of the slump. Normally, we can be consider 50 mm slump. It is specified. Now come to the step 2, maximum size of the aggregate. Normally, whether they mention or not mention, we should be assumed that size of the aggregate which will give maximum strength of the aggregate we can be take is 20 millimeters. Now estimation of water content and also the air content. Water content and air content is purely based on selection of water content and air content is purely based on slump 50 mm what we have assumed, size of the aggregate 20 mm or 90 mm which we assumed. There we can be get the value of water content. Now for the selection of water content, we can be refer this table. Slump we assumed is 50 millimeters. So here size of the aggregate we have taken is 19 millimeters or 20 millimeters. So from the tabular form, It is shaded with a yellow paint. You please observe this value. The quantity of water that we can be collect from the tabular form is 190 kg per meter cubed. Now here selection of water cement ratio. So already we have discussed in the methodology, it purely based on the compressive strength of the concrete. Now you refer the table, we know normally specific gravity of the Portland cement we can be take is 3.15 and fineness, the specific gravity of this blast slag we know is 2.90 and the specific gravity of the fly ash we can be know from the code is 2.30. Now you see the tabular form. So here selection of water cement ratio for two conditions. One is the non-air entrained concrete. Second one is the air entrained concrete. Suppose if the compressive strength of the concrete is 50 megapascal or 50 Newton per millimeter square, for non-air entrained concrete, the water cement ratio that we should be considered is 0.48, whereas for the air entrained concrete, so here normally the water cement ratio we can be take is 0.40. But in this problem, the compressive strength what we have taken or maybe they have given in the problem is 50 megapascal. So for this problem, for non-air entrained concrete, for a compressive strength of 50 megapascal, the water cement ratio we should be considered is 0.48. You can be observed from the tabular form. Now come to calculation of the cement content. So already we know the value of water cement ratio we collected from the tabular form, it is 0.48, and also we know the amount of water which is required to make an excellent concrete. The value we collected from the tabular form is 190 kg per meter cubed. So we know that water cement ratio equals to water by cement. Therefore, amount of cement which is required for us in terms of kg per meter cubed is amount of water divided by water cement ratio. You see the calculation which we have shown in the step 5. So 190 divided by 0.48, that will give 395 kg per meter cubed. And next part is estimation of the coarse aggregate. So here in the problem they have given the fineness modulus of the fine aggregate is 2.60 and a bulk density for a 20 mm size of the aggregate is 1600 kg per meter cubed, whereas the amount of coarse aggregate for volume of the concrete is 0.64 times of the volume of the concrete that we can be see in the tabular form. You please say now the size of the aggregate that they have given the problem is 20 mm or we assumed is 20 mm. If the fineness modulus of the aggregate is 2.60, so the amount of coarse aggregate or bulk volume of the coarse aggregate equals to 0.64 times of volume of the concrete. So here the calculation of this or maybe value what we are considered here, it purely based on the size of the aggregate and also fineness modulus of the aggregate. Now come to estimation of the fine aggregate. Here first of all we should calculate volume of the each ingredient which was present in the concrete. You know the ingredients which were present in the concrete are number one cement, second one coarse aggregate, next one fine aggregate, and the last one is the water content. Now here volume of the water. How we can we know the volume of the water? So here volume of the water equals to amount of water which is required for the concrete divided by density of the water, that will come 0.19 meter cubed. Now come to volume of the cement. So specific gravity of the cement that we have taken is 3.15. So the volume of the cement equals to amount of the cement 395 kg per meter cube divided by 3.15 into 1000. That value will become 0.126 meter cubed. In the same way, volume of the coarse aggregate is 0.396 meter cube. The calculation was shown there. And also volume of the entrapped air. Entrapped air they have mentioned is 2%. The volume of the entrapped air will comes about 0.020 meter cubed. Now we know all the volumes. All the volumes are ingredients of the concrete. Now we should be calculate the volume of the fine aggregate. So here, so except the volume of the fine aggregate, we know all the volumes which was presented in the concrete. So here volume of the fine aggregate equals to, so total volume of the concrete equals to volume of the water plus volume of the coarse aggregate plus volume of the cement, that will comes about 0.732 meter cubed. Therefore, volume of the fine aggregate will comes 1 cubic meter minus 0.732, that will comes around 0.268 meter cubed. Now here mass of the fine aggregate equals to, we know specific gravity equals to weight divided by volume. Therefore weight equals to the product of specific gravity and volume. Therefore mass of the fine aggregate equals to specific gravity of the fine aggregate into volume of the fine aggregate, that will becomes 0.268 into 2.58 into 1000, that will be 690 kg per meter cubed. Now we calculated, already you are very perfect in that, we calculate volume of the cement, volume of the coarse aggregate, volume of fine aggregate, and also volume of the water. Now we should see the mix here. Water equals to 190 kg per meter cubed. Cement content which is required for the concrete is 395 kg per meter cubed. Coarse aggregate 1020 kg per meter cubed. Fine aggregate 690 kg per meter cubed. And density of the concrete we know is 2295 kg per meter cubed. Thanks for watching.